Hey guys, let's talk a little bit about power. We're going to talk a little bit. I'll do a couple problems and then point you off to some readings, and then you'll have some practice and do your assessment. Anyway, think about walking up the stairs at school. So say you're coming into school and you're early so you can walk up to class up on the fourth floor, versus one day when you're late and you need to run up the stairs in order to get to class on time. Why do you think it's easier? Does it feel easier to walk than it is to run? Because after all, when you go up the stairs, here's some terrible stairs. You're here, right? When you go up the stairs, if we talk in terms of energy, you've increased your potential energy, your gravitational potential energy, the same whether you're walking or running. So why does it feel harder? Well, that has to do with this idea of power. And so here, walking, the work that we do when we walk is equal to the work that we do when we run. And the work here is going to be the change in energy. So when you're walking or running, you're taking internal energy and it's being shifted over into gravitational potential energy. So because you're taking like your metabolic from your eating and you're using oxygen and all this stuff's going on internally, and you're changing that into gravitational potential by the time you get to the top. However, the total work that you do is the same. So why is it harder? And this has to do with an idea called power. And so we'll define power. Power is going to be the amount of work that you do over time. And this is the key part. Less time means more power. So when you run, you're doing the same transfer of energy, but you're doing it a lot faster, which results in a greater amount of power. So you can see here for the power for walking, you would have some work that you did divided by, say, it took 5 seconds. Whereas when you run, the power when you run would be the work, but maybe you did it in 2 seconds. So you can see the power when you walk, if I break that out, that's 1/5 of whatever the work you did. And the power when you run is 1/2 of the work that you did. So you can see 1/2 is greater than 1/5. So clearly running, it requires more power when you're running up the stairs in terms of work. The units for power, so the standard units that we'll be using is the watt or watts. We use a W for that. It's different from this one, work. And in the United States, we also use horsepower, or HP. And 1 horsepower is equal to 746 watts. So if we wanted to get something into horsepower. And then watts, what it is it's your, since power is work over time, it's going to be joules per second. So it's how much energy we use every second. That's called a watt. So let's do some examples. We'll do a couple. Janie's doing a deadlift. Deadlift's when you take a barbell and you lift it straight up. So, kind of holding on to a barbell, and is going to lift it straight up. And so that change in height right here is going to be 0.7 meters. And the time that it takes to do that is going to be 0.08 seconds. And the mass of the mass is going to be 13.6. So we want to know the power. So then we say, well, power is going to be my work divided by time. So I'll have to use that, but I need to know the amount of work done. So thinking about the initial state, if we want to figure out the work. So let's do our work energy plus the work is going to be the final energy. So the initial energy that this thing has is 0. There's no potential energy, no kinetic, so there's no energy. So this just simplifies to the work is going to be the final. After you lift this up and holds it up here, we see that we have some gravitational potential energy. So my work is going to be mgh. So coming back over here now, my power would be mgh divided by delta T. So we get 13.6 times 9.8 times the height, which was 0.7, divided by the change in time, which was 0.08. So the power that she used to lift that barbell was 120 watts. One note, we talk about magnitude. I didn't write it, but normally we'll be talking magnitude. You won't have a negative on power. So 120 watts. If I wanted that in horsepower, I could divide by 746, but that's not necessary. So now let's say she does that, but then she keeps on lifting it, and she lifts it up over her head. So she's going to lift the barbell from here up over her head. So I can redefine my reference line for my gravitational potential. So all I want to know is this 1.3 meters. 1.3 meters. The mass is the same. It was 13.6, and it takes her, change in time is 1.3 seconds. So I want to know the power. So power is going to be work divided by the time. The work that she did here, if we could go through the same steps, it'll be like this. There's no initial energy unless you defined it to be down here at the bottom, if you're counting this. But we're just going to put this as a reference line. So the power is going to be, again, mgh divided by delta T. So you can just substitute the values in. I'm not going to finish that one. It's pretty clear. Okay, here's a different one. So we have a car traveling on a level road at a constant speed of 27 meters per second. Let me go ahead and sketch it out first. So there's my car. It has a velocity of 27 meters per second. And we'll say it's moving in this direction. Just keep things easy. So on a level road. Okay, the drag force exerted by the air on the car and the rolling friction force exerted by the road on the car. So the drag force of the air and the rolling friction is it has to do with the tire rotating. We'll talk about more of this when we do rotation. But rolling friction is opposite to the motion of the car. So rolling friction is going to be in this direction. Air is going to be in this direction. So what we have is they add up to be this, and we'll just call this the frictional force. So we would have the frictional force is in this direction, and that's equal to 680 newtons. Okay. Motion of the car. Determine the rate of work. So the rate of work, that's power. The rate of work done, because it's work over time. Done by the air and the road. So we want the work done by this. Express the answer in watts and in horsepower. So this one we'll have to transform. So going to power, well, power is going to be work divided by the change in time. And now remember, there's our other definition for work is, well, it's change in energy, but it's also the force times the distance or the displacement over time. Delta T. And so we know the force is the frictional force, but this distance, the distance is built into here. See how this is distance over time? So I could rewrite this. Force is going to be my displacement over time. And in 1 second, this car goes 27 meters. So I would have 680 times 27 meters in 1 second. And so I'll get 680 times 27, which is 1.8 times 10 to the fourth watts. And then you divide that, so there's my answer in watts. And then to get it into horsepower, we would just do 1.8 times 10 to the fourth divided by 746. And that would give me 25 horsepower. So that's the amount of power that the air and rotor are exerting on the car. So again, this is just, we can use this, we can do change in energy, or we can do force and distance. Go to OpenStax, that's the online textbook, section 7.7, just read that. There's some practice problems there. Some of them have the solutions. I think I have it open. And that'll be it. Let's see, here's 7.7. So you can read about power, has some examples. When you get down to the questions, there's some examples of how much energy is used by, or how much power by certain things. So say, I don't know, electric clock, 3 watts. Power and energy consumption, you can read a little bit about that. And then down here, when you get to the questions, if you've never looked at this, so like here's a question, you can work it out, and then you can actually just see the solution. So it doesn't have it for all of them, but some good practice. Anyway, there you go. So practice, take your assessment, and that's it.